In this video, I'll explain you how does potential varies with respect to position from a charged sphere. Now, a charged sphere has charges on its circumference. Okay. With respect to point charge, I have already told you what will be the potential at a distance A, which is measured at r distance away from the source charge. The value of potential is 1 by 4 pi epsilon 0 into source charge divided by RA, that is the position vector, or the position or the distance in between, shortest distance in between these 2 points. This is the potential at VA with respect to a source charge. Now, this is a shell. We have 3 different positions. One is this one, and another one is this one, and another one is this one. So case 1 is any point in, I'll take case 1 as this one, any point outside the shell. So case 1, outside the shell, outside the shell. This is very important, okay. Case 2, on the shell, and case 3, inside the shell. Okay, outside the shell, how can we get the value? We know the very important equation, that is E is equal to minus dV by dr. Okay, so from here we can get the value of V. How we will get the value? dV is equal to E into dr, minus of E into dr. Now how can we get the value of V? Integrate it. So integral dV, integral dx is x. Similarly, integral dV will be equal to V itself. Okay, now why I have used this equation? Because I know E. I know electric field at a point of distance, maybe I am going to take the distance as RA away from here. What is the electric field due to a spherical shell at a distance of RA from the center? The equation for electric field is nothing but 1 by 4 pi epsilon 0 q by r square. So at a distance of RA away from here, this will be the value of electric field. This we have learned in the chapter 1. Okay, now I am going to substitute this equation here. So integral dV is equal to V, which is equal to integral of electric field 1 by 4 pi epsilon 0 q by r a square. Now this has been derived with Gauss's theorem. Okay, so if you don't know how we have got this equation, go back to chapter 1 and get this equations done. Okay, now this into dr. So here anyway integration, right? So I'll take arbitrary position r. Now V is equal to, integrate it, I can take common term outside, 1 by 4 pi epsilon 0 q by and 1 by r square, that is r power minus 2, integral 1 by 4 pi epsilon 0 q by, what is the integral of this? R power minus 1 divided by minus 1. And I already have a minus here, yeah, minus here. So this minus and minus will cancel, and the value will be 1 by 4 pi epsilon 0 q by r, that is the integral. So same equation, we have learned the equation with respect to point charge for shell also at a distance of, any r away from the center outside the shell, that this is case 1. At a distance of r away from the center outside the shell, the value will be the same value as that of point charge, a point source charge. And next I will explain you what will be the case 2. Before case 2, we will go to case 3. Case 2 I will explain. Case 2 is very simple. Let me explain case 2 itself first. Okay, so case 2 is nothing but we are on the surface. What equation we have learned? Outside the surface, 1 by 4 pi epsilon 0, just now we have learned, right? Q by r. R is nothing but the position which is measured outside the shell. This is the potential outside the shell. Clear? Now whenever we are on the shell, what will be the value of r? on the shell, that will be 1 by 4 pi epsilon 0 q by r measured from the center will be nothing but the radius itself. So q by capital R, where capital R is equal to radius. Make a note of this. So V at surface. Okay. Now how does this vary? This is the equation at surface. Now when we go outside, the equation will become V outside is equal to 1 by 4 pi epsilon 0 q by r. Now from surface, when we go outside, surface the values r, the value is less. When we go outside, the value of r increases, right? Which means this increases, which means potential decreases. As r increases, potential decreases. Now we know we only have derived or got the values at two cases. One is at center. So let's say this is our center. Okay, and we got this is surface. Surface means at a distance r away from the center. Then this is at r, and this one is any value outside the shell, that is value of r greater than capital R. Now at surface is the maximum value. What is the value? 1 by 4 pi epsilon 0 q by r. Now after that it decreases. Now one more part is remaining. What is that? From center till r. Okay. Now we have to use the first equation. What is the equation? We have learned E is equal to minus dV by dr. Now why I have used this equation? Why can't I substitute in this equation? Because here the electric field, in this case also electric field is the same thing. What is the equation for electric field? 1 by 4 pi epsilon 0 q by r square. Now on the surface also I can substitute this equation, where substituting the value of r as radius. Even outside also I can substitute the value of electric field as this one, where r will be the distance measured from center to that point. But inside we know electric field is 0 from Gauss's theorem. So I can't use these two equations. I have to derive the value of potential at inside the shell in a new method, where electric field is taken as 0. Now it's very simple. Case 3 where the point is inside the shell, where electric field is equal to 0. When electric field is 0, 0 is equal to minus dV by dr. Multiply dV is equal to 0. dV means the potential difference in between any 2 points. Potential difference in between any 2 points inside a shell, if it is 0 means it's constant. Clear? It's constant. Constant means potential at here and here is same. Correct? If the change in temperature is equal to 0 means final temperature minus initial temperature is change in temperature, that is 0. So Tf is equal to Ti. Final temperature and initial temperature are the same. And inside the shell, potential difference is 0, which means potential is same. Same to which value? Same as that of surface. Clear? So inside, from center, when we are coming out, potential will be same, constant till the surface. Okay, after surface it decreases. So this is the value. See, from center till surface the same potential, 1 by 4 pi epsilon 0 q by r. Why? We have derived there is no change in potential any point inside the shell. The value is same as that of potential at the surface of the shell. Clear? Now from here when we go out, the potential varies with this equation. So this is the potential outside the shell, this is the potential on the surface, and this is the potential difference inside the shell, which is 0, which means potential is constant throughout the shell, which means it's an important there is an important takeaway from this. We know that work done is equal to Q into potential difference. Clear? Here in this case, if we are moving a charge of Q from here to here, or from here to here, or from here to here, anywhere inside the shell, the potential difference is 0. Whatever the potential this charge have at this position, it will be the same potential here. It will be the same potential here. It will be the same potential here. So what will be the work done? Q into potential difference, 0, which is 0. Which means if you are moving any charge from one position on the surface to another position on the surface, it is 0 because there is no potential change. We have learned it. And even when you are taking a charge from here to here, the value is 0. From center to outside, the work done is 0 because there is no change in potential. Work done is equal to change in potential of these 2 points from final minus initial into the charge we have moved. Here the potential difference becomes 0, so the work done will be 0. But that is not the scenario with respect to outside, where potential decreases. And this is the graph for variation of potential with respect to a charged shell. And we have learned variation of electric field with respect to shell in the first chapter. Compare these two and study. Thank you.